Hello, um, this is from 2018 and the tutorials aside, this is my first attempt to train a network. This neural network looks a bit different because of a couple of reasons. First, there's a graphical interface, and the second, I don't use traditional methods like backpropagation, but instead I use neuroevolution for this network. Pink circles are my agents. The red one is the most successful one. They basically chasing after the food because they need food to live more than 400 frames. 400 frames are their lifespan. After 400 frames they die, or they need to touch the green circle again. So there's another rule, but they don't know about it. If they leave the area, they just die. The input of the network is very limited. They only know about their x and y coordinates and the x and y coordinates of the food and the distance between them and the food. That's all. Only 6 of them, x, y coordinates. They don't know about the radius of the circle or the border of the area. If they cannot touch, they die. They leave the area, they die. That's all. So, and there is no other reward scheme that we usually use for reinforcement learning algorithms. For this environment, I use two different libraries. So the first one is P5.JS. P5.JS is a JavaScript library for creative coding. It is great. If you have time, just check it out. It's a great library. And the second one is tensorflow.JS. Tensorflow.JS is a TensorFlow, but just works on your browser. It's very easy to start. Also, I have some parameters here. For example, this one for controlling minimum population size. If my population is under 5, for example, new agents spawns, so I can control this. Now I have, I guess, 10 of them. Let's push this number a bit to, let's say, 20 or something. Yes, now I have more agents. These agents weights comes from the most successful agents. If you check my code, you will understand. And also I can control the incoming population size. For example, now it's about 20 or something, and I can change the food size very easily. Although they don't know about the food size, radius of the circle. And I have learning rate here. It's not a real learning rate, but this is how much I change the weights of an agent. It's a hyperparameter, so which is not, it doesn't have any certain value. So, and the mutation change of a weight is 1% to 15%, is about what percent of the weights should be changed. So you can push it to 15%, which is a bit destructive. There's a sweet spot around 4 or 5. And the best before is a best before date for the food. The food stays in this area for a 300 frames to 1000 frames. I can change easily from here. For now, the food stays here, for example, 500, as far as I remember, 500 frames. Frames are here, as you can see. Once it will become 500, it just randomly pops up somewhere else. There is only one way to interact with the environment. I can drag this food over different places in the area, um, and the agents follow it. So I can change it and create some disturbance in the environment here. Their actions are very similar, but time to time I manage to see different kind of behaviors. For example, some of them try to find the shortest path between them and the food. Some others just circling around the food. These kind of behaviors were possible. But unfortunately, at that time in 2017, 18, I didn't know how to save a model, so I don't have any proof for that behaviors. I cannot show you. Maybe if you want to use my code, you can do it by yourself. It's possible. I'll make my code available with this video. And I should warn you, it's a bit messy. In fact, it's here. So it's only one file, two files, one HTML file and one JavaScript file. In the HTML file, there is a link for P5 and also for TensorFlow. These are my sliders for the JavaScript. Pretty messy code, but somehow it works. Maybe I can mention about the process, the mutation process. If a population is under a certain amount, you can change it. I take the last, let's say 10 of them. There's a kind of randomization, and I pick their weights, the weights of the agents, then create new agents out of them, and I put a little bit mutation. The mutation code is here. It's a basic random Gaussian mutation with the learning rate, and that's all. And when new generation spawns, they will get that new weights based on the most successful agents from the previous generation. There's a couple of surprising catch for me in this experiment. One of them is the agents can learn implicitly about the borders. They tend to stay in the borders. So I don't feed the agents with the coordinates of the edges, but they still tend to stay in this area, which is interesting. They don't know about the radius of the circle. Again, they tend to be close to the center of the circle here. It's interesting. I try to keep inputs very limited. They have only six inputs, xy coordinates of them, food, and the distance between agent and the food. That's all. In fact, 3 of them, but as a xy coordinate, it's 6 of them. And the last one is a bit different. It's a bit, again, surprising for me. If you push the population size to higher numbers, let's say incoming population number to 300, let's say to push it this way. So there's a diversity here. But the problem with this environment, individuals here, agents, tend to be lazy. So because just think about that, if there are lots of agents around here and this one, closest ones, doesn't do anything when I change the location of the food, the other just touch the food and the genetics of that agents could be passed to next generations easily. So there are some sweet spots for the numbers, the size of the area and this kind of stuff, which is a bit surprising for me, and also make made this experiment fun. I hope you like it. If you have any questions, please ask me directly. I will put my information in the description. Thanks for watching.